So this is our first introduction to our new unit on atomic structure and periodicity. So we're going to introduce these topics by first understanding where the current model and understanding of the atom came from, where it arose from. And we're going to talk about first the wave nature of light and quantization. Okay? So the idea is all light can be perceived as either a particle or as a wave. For now, we're going to focus on light being viewed as a wave. Okay, and what you see in front of you are examples of different wavelengths that we are familiar with in everyday life, including the visible spectrum, which you see here, from 400 to 750 nanometers. We have X-rays, gamma rays, infrared, radio frequency. You might have heard of all of these being considered waves. So what does that actually mean? Well, when light travels, okay, from a light bulb to our eyes, or when a radio signal travels from the station to the antenna on your car, there is an actual wave that is traveling through air or whatever medium there is. And we can model that wave, okay, with a diagram that looks very similar to kind of like a sine curve or cosine curve, okay. And for every wave, each wave has two different properties. It has something called its frequency, and it has something called its wavelength. Okay? The wavelength is essentially just the length of the wave. How physically long is it? You notice the units that we measure wavelength in are in meters. So what you see on this diagram are the lengths in meters of these different waves, common waves. So radio waves are 10 to the third meters long. That's a very, very long wave, whereas gamma rays are 10 to the negative 11th meters long. They're very, very small and very short. However, you notice that radio waves, okay, have a very, very small frequency relative to the frequency of gamma rays, on the order of 10 to the 20th versus only 10 to the 5th down here. So what does that actually mean? Well, all electromagnetic waves, light waves, move at the same speed. And so we can use this information and knowledge to determine information about electronic structure of molecules and atoms. That speed, which we abbreviate with c, is the speed of light, which for our purposes is about 3.00 times 10 to the 8th meters per second. Okay? And the relationship between any wave's frequency and wavelength is represented by this equation. C equals lambda, which is the symbol for the wavelength, times nu, which looks like a V, Greek letter, and that's the symbol for frequency. Okay, so this is an equation we need to be familiar with, where this stands for frequency and this stands for wavelength. So any wave is related to the speed of light. Their frequency and wavelength are indirectly related because they're always equal to the speed of light. On this diagram, let's point out real quick, what would be the wavelength? The wavelength would be the distance from one part on the wave to another part on the wave that looks at the exact same. So here it's at the top to the top. That distance in meters would equal lambda. The frequency is how many cycles per second. If you notice, the units here are s to the negative 1 over seconds. So how long does it take for this to occur? How many times can that pathway right here occur in 1 second? That's the frequency. Okay. And if you notice, the higher the frequency, the shorter the wavelength. The longer the wavelength, the shorter the frequency. Okay. This is some basic information. We'll do some, mathematical problems with these relationships tomorrow. But we also need to recognize what this insight, the limitations of it, were for scientists in the early 1900s. So this is where we're going to focus on the idea of quantization. Okay. So that relationship between wavelength and frequency explained a ton of everyday phenomena about waves and light. But there were a couple things that it didn't explain, and one of those was black body radiation. And you don't really need to know about what black body radiation is, But one guy took some particular notice to it. His name was Planck, okay, last name Planck, Max Planck, and he noticed that when you took a light bulb and you heated it up, the amount of energy that was released depended on its temperature. And the frequency and wavelength weren't the only two things that, determined the properties of this light. So he, through a bunch of theory and experiments, came up with a relationship between the energy of a wave, an electromagnetic wave, light, and its frequency. And that relationship is energy equals h, which is the Planck's constant, times nu, the frequency. So this again is our frequency, and this is Planck's constant, which is equal to 6.626 times 10 to the negative 10 to the negative 34th joules per second. Okay? So this is a very profound thing for Planck to notice. Okay? Because what this is telling us is there is some amount, some specific constant, some number, specific number that relates the energy of a wave to its frequency, how many cycles per second it's occurring. Usually we think of energy as something that just exists continually. Someone can have, any amount of energy from 0 up to infinity, whatever we want to call it, okay? But what this relationship tells us is that energy only exists in discrete amounts, specific amounts, which Planck called quanta, or quantum is a singular, okay? Energy can't just exist from 0 to 100 in any number. You can't just release from a wave. A wave can't just have 0 energy anywhere up to 100 and any amount in between. Okay? It can only have discrete amounts. So it might only be able to have 0 joules or 5 joules or 50 joules or 100, but nothing in between. Okay? And a better analogy for this is maybe this picture down below of quantization. So let's say this guy is walking up some stairs. Okay, he has to go from the bottom to the top. And he has, at any given point, a certain amount of potential energy, PE. Okay? And what we'll do here is we'll just draw a little graph, or we'll just label this axis as E, the amount of potential energy he has as he goes up. As he climbs higher, his amount of potential energy increases. But what we notice here is in the first diagram on the left, A, this guy only can have certain amounts of potential energy. So when he's on the first step, he has this amount of potential energy. When he's on the second step, he has this amount. On the third step, this amount. Fourth step, this amount, etc., increasing. But these spaces in the middle, he can't exist, he can't stand between the two steps. He can only stand on one step, or one above or one below. His amount of potential energy can only be on these discrete quanta, these small packets, specific amounts. This is what Planck noticed. This is his observation. Planck is that light exists, the energy of light waves exists in discrete quanta, specific amounts. What doesn't happen is what we would expect to happen is, here's the ramp, he can stand anywhere on this ramp. There are no limits to where he can stand, and anywhere he stands, he's going to have a specific amount of potential energy. This whole thing is kind of like a gradient. He could stand anywhere on here. But what Planck noticed is that's not actually true with light. Light only exists in very discrete quanta, discrete amounts. Okay. We're going to talk about later this week how we can use this information to determine structures of the atom, okay, by seeing what kind of light and energy they release. What you need to walk away with today is the idea of what quantization is, Planck's relationship between energy, frequency, and Planck's constant, what Planck's constant is, and knowing what frequency, wavelength are, and the speed of light, 3.00 times 10 to the 8th meters per second, and the relationship between them as given by this equation.